Hello and welcome to Differential Equations. Today is March 21st, 2020. We're in springtime now, it's official. And today we're going to do section 1.5. This will be the first of several videos because I might split it up. I think I might do a different video for every example problem I do. So this video, I'm just going to summarize and point out some of the most important parts of what you should have read from section 1.5. By the way, today's Saturday, and I'm coming to you live from the Johnson household. So you can see the kitchen is that doorway right behind me. Got the light coming in from this window over here. It's beautiful. I want to point out to you here, this is the type of equation we're dealing with today. And the key elements to look for is that there's no x's, except there's just one x right there. Everything else, like you can have any sort of crazy stuff with t, crazy stuff with t, but this is the type of equation we're dealing with. It's called a first order differential equation because there's only one derivative. So if there's two derivatives, it's a second order differential equation and so on. All right, now this book does a lot of applications, and my advice to you is to try to be curious. So if it's telling you about mine tailings, then for that day, you care about mine tailings. If it's telling you about a spring, then for that day, you care about springs. You just gotta care about it enough during this section, and that'll help you to do better as far as learning things more. If you just tap into that curiosity that's been crushed out of you from the educational system and try to be curious about what's going on. So this is a thing that's pretty common in, I mean, I'm no expert on mining, but I believe this is something that's pretty common, which is when you're mining, you've got all this excess stuff and you want to deal with it. And if you're in a developed country, you probably deal with it in a way that doesn't pollute everything around you. And so you don't have to know much about mining. It's just like this is sort of thing. The derivative is rate in minus rate out. It happens again and again in this class. And so then you figure out, well, what's the rate in? That's 5. And the rate out is kind of a fraction of the amount in the lake. And then the amount of the volume of the lake is getting smaller with respect to time. So then you can write it, so going from writing it this way, so this might be a problem that you might see in the homework. What you need to do is write it this way so that there's a dx over dt, something that's only in regard to t, x, and then something that might be constant or a function with regard to t. Now, a trick they do here that we'll eventually in this section learn how they came up with this is that you multiply both sides by this thing. Okay, don't worry about how they got that, just know that they multiplied by that thing. And so, after they multiply by that thing, I need a little more room here to show the equation. After they multiply by that thing, they have this left side now looks like this. Okay, so now notice that the power here is different, -20 and -21. So then notice now that this looks a lot like, this right here is what you would get after doing a chain rule or a product rule. And so then, because it's the product rule of having taken the derivative of this term, and after taking the derivative of that term, you get that. So instead of having all of that, you substitute it as its derivative of this term. So instead of having two terms, it's now the derivative with respect to t of this term. And it's a product rule because x is changes with respect to t. So you just, you don't know what that'll be, so you just say leave it as dx dt. So then you've got this here, and then you can integrate both sides, which is a trick we use a lot in this class. So integrating both sides and simplifying gives me this expression, and then I've got a starting condition, so I can plug in c, And lo and behold, look at that. This is the pollution in the lake. Until there is no water left, so there can't be any pollution in it. Another thing I want to point out is that it can be really beneficial to, as you're reading the textbook, have a piece of paper over here and kind of doodle or even do some of the equations. If you oftentimes when you're just trying to read a textbook like you would read a novel, you're not going to remember as much. So trying to have a piece of paper out and doodle and sort of do some of the equations they do can really be helpful. Okay, now here 1.5.2, they handled the situation where instead of a function of t and a function of t, they were constant. And so if they're a constant, you can multiply both sides by this term, which again, we'll figure out why that term is there in a second. And and then here's equation, example 5.2, example 5.3. They're both really good. I recommend trying them and figuring out how the SAGE works. I'm going to jump to this right here. So this is where they do it in general. Okay, so in general, you have your x prime equals p of t. No, x prime plus p of t times x equals q of t. And then you want a thing whose derivative is p of t. Okay, so like I choose p of t such that capital P prime of t is little p of t. Okay, and then multiply both sides by e to the power of capital P t. And then notice that the derivative of that is product rule. So e to the p of t times x prime of t plus little p of t. Notice because that's the derivative because you're doing chain rule there, times x of t. Okay, and that's equal to e to the p of t q of t. I'm losing it. Okay, integrating both sides gives you e to p of t times x equals the integral of e to the p of t q of t dt plus c. So then x equals 1 over e to the p of t times the integral e to the capital P of t times q of t dt plus c. Now, what we call this mu of t is called the integrating factor, e to the integral of little p of t dt. And then something we do in math is that when we get so much like going into exponents and such, where we have to use a smaller font, sometimes it's simpler. That means the same thing as exp of the integral of p of t dt. So that's our integrating factor. And that means that x of t equals 1 over the integrating factor times the integral of the integrating factor times q of t plus c. And so right here, this, the thing that they basically did in every single example up until this point, you can do in general. And when you do something in general, then it gives you a formula. So this is basically how you're going to solve all the problems in this section. Is that this is called right here, this is your integrating factor. And then you use the integrating factor in this formula. And that gives you the answer. Okay? I recommend going through all the examples, but I'll now start creating some videos for the different activities from this section.